All right, so we're in 10.4 now. And 10.4 is kind of a large section. So we're going to be spending some time here. The idea is, now that we have talked about what polar coordinates are and how to do some converting back and forth between polar and rectangular coordinates, we're now interested in what the graph of polar equations looks like. So we've, up until this point, throughout all of your algebra that you've had, you've looked at the graphs of a variety of different functions, you know, lines, parabolas, logarithms, exponential functions, and even in this class, sine, cosine, tangent, all the trig functions. But so far, all of those have been thought of in terms of rectangular coordinates, things with an x and a y variable. Now what we want to look at is what a graph of an equation would look like if the variables are r and theta, you know, things in polar coordinates. And so before we get into specific graphs, because there's several specific types of graphs that would be new to you as of this section that we're going to look at, we want to look at some of the basic properties that might be present in a graph of a polar function. So one thing that we actually spend some time, and we've done this in this class, we've spent some time investigating, is symmetry. In the case of rectangular coordinates, we talk about even and odd symmetry, symmetry about an axis, or symmetry about the origin. And we have similar types of symmetry here, but the relationships are different when things are written in polar coordinates. So the idea here is that we have some equation where the variables are r and theta from polar coordinates. And I want to look at, if I were to replace either the r, the theta, or both with something else, if the resulting equation is the same as what I had started with, then that should imply some kind of symmetry. So that's very vague right now, but we're going to investigate three types of symmetry. Symmetry about the horizontal axis, which again we call that the polar axis. Symmetry about the vertical axis, which is the line theta equals pi over 2. And then symmetry about the pole, which is the same thing as symmetry about the origin. So to start with, I have these polar grids here, and I just want to look at what happens if, for example, I choose some point here. Okay, I'm going to call this point r theta. Okay. Now the first thing I want to do is investigate what the mirror image, or what the reflection of this point would look like if I had reflected it across the line theta equals pi over 2, so the vertical axis. That's like a reflection across the y-axis if we were thinking of this in terms of polar or rectangular coordinates. So that's going to take me to this point right here. Okay, now what is the relationship between these two things? Well, there's a couple of ways of thinking about this relationship. I would expect, so here's a little line segment representing r, right? There's r right there. I know that the line segment here would also be thought of as r. But what's changed from this point to this point is theta. If I'm calling this theta right here, then this new angle is something different. And there's a couple of ways of coming up with that angle, but what I want to do is think of getting from this point to that point in a series of two steps. The first thing I'm going to do is actually not reflect this point across the vertical axis. I'm going to reflect it across the horizontal axis, or the polar axis. In other words, what is this point down here, and how does it relate to this point up here? Well, again, the length of that line segment there would be r, because I haven't changed the distance between these 2 points and the pole. What I've done is I've changed the angle. But by reflecting it this way, I could see that this angle here could actually be thought of as negative theta. Okay? Now, you can see that this point and this point are lined up with each other. They're on the same line through the pole. So if I were to reflect this point through the pole, or you could think of it as rotating it 180 degrees, it would take me to this point. But we know that when you have a point in polar coordinates, this would be the point r negative theta right here in polar coordinates. If I were to reflect that from here to here, that's the same thing as taking the r and making it negative. So, and then keeping the angle the same. What that tells me is that this point can be thought of as having the coordinates negative r, negative theta. So in other words, if I want to obtain this point from the original point, then what I can do is take the opposite of r and theta. Taking the opposite of theta takes me down here. Taking the opposite of r shoots me up here, getting me to this point. Okay? So r theta, if I change that to negative r, negative theta, it'll reflect this point across the line theta equals pi over 2, the vertical axis. Now the idea in terms of symmetry is if I'm given an equation in in polar coordinates, if we have symmetry about this vertical axis, then for every point on this side of the of that axis, I should have a corresponding mirror image of that point over here. So in other words, if I was looking at the graph of a polar equation, which we'll do a lot of after we talk about symmetry, I should be able to take the point r theta and replace it with negative r, negative theta, and the result should be another point that's still on that graph. That gives me a symmetry test for symmetry about the line theta equals pi over 2. Okay, let's look at the case of symmetry about our polar axis. That's our horizontal axis. So once again, I'm going to look at a point that I'm going to call r theta. Okay, and I want to see what would happen if I had taken this point and reflected it across the polar axis. Well, we've kind of already done that over here. We've seen what that relationship looks like. It's just taking the angle theta. Let me draw that in. And here, let's go like this. There we go. Keeping r the same. So if this is r, this will still be r. But instead of looking at theta, we look at negative theta, the opposite of theta. Okay? So if I were to take the point r theta and replace only the theta with its opposite, that should give me a mirror image or a reflection of this point across the horizontal axis. Okay? Now there's another way of thinking about getting from this point to this point, and it's kind of similar to what we did over here. So if I were to start by taking this point and reflecting it first across the vertical axis, so that takes me to here. Well, what I want is this angle right here. We didn't think of this angle in the previous example, but if you think about it, by the symmetry of this thing, if this angle here is theta, then so is this one. But this entire angle right here is pi radians. So if I do pi radians minus the theta that I would get right here, this angle can be thought of as pi minus theta. And then I still have r here. Okay, then to get from this point to this point, I would keep the angle the same, pi minus theta, but take the opposite of my r to create that reflection. So another way of transforming this point, or sorry, not transforming, but of reflecting this point from here to here, is to take the opposite of r and change my angle to pi minus theta. Now, this is going to be an alternative to this, but you're going to see that we don't really use this one very much. This is easier to use when we talk about our symmetry tests, which we'll do an example of on the next page. Okay, let's look at one more. When we talked about symmetry of equations for rectangular coordinates, even in odd functions, we talked about odd functions as having symmetry about the origin. And the idea there is that you have a point, and again, this is going to be r theta now. Okay, so that this is theta right here. For symmetry about the origin, we think of that as reflecting this point first across the horizontal axis and then again across the vertical axis. Notice that's going to take me to this point. Oh no, I missed it, sorry. This point right here. Okay. Well, there's two ways to get from this point to this point, but for the purpose of this symmetry test, we're only going to focus on one. Notice that this is a 180-degree swing from here to here. So if I keep theta the same, but take the opposite of r, that should get me from this point to this point. So taking the point r theta and changing it to negative r theta should produce this point from this one. And again, if a graph is going to have symmetry about the pole, then for every point over here, I should have another point that can be obtained by reflecting this one through the origin, which means across the horizontal and then across the vertical axes. Okay, so this leads to our 3 symmetry tests. This is from your book. So it's 3 symmetry tests for polar equations. And I know this is small, but this is just reiterating what we've already said. So a graph is symmetric with respect to the line theta equals pi over 2. Remember, that's the vertical axis. If replacing r theta with negative r negative theta yields an equivalent equation. The implication there is, again, like we said, making that replacement for any point on the graph of that equation should produce another point that's a reflection across that line and is still on the graph of that equation. But the symmetry tests make it so we don't have to be looking at the graphs explicit. We don't have to be looking at an image of the graph to be able to tell if we have this kind of symmetry or not. So what I'm going to do here is test the equation r equals 2 sine of theta for symmetry. And I'm going to check for each type of symmetry that we talked about. Symmetry about the line theta equals pi over 2. Symmetry about the polar axis. And symmetry about the pole. So for symmetry about the line theta equals pi over 2, we have this symmetry test. We replace r with negative r, theta with negative theta. So taking the equation that's written here, I'm going to replace the r with negative r, replace the theta with negative theta, 2 sine of negative theta. Okay, now because sine is an odd function, we know that the negative can be brought out. So I go like this. This becomes negative r equals negative 2 sine of theta. And then because both sides of this equation have a negative, I can divide everything by negative 1, which produces r equals 2 sine of theta. And if you notice, the end result is the same as the original equation. This is what it means when it says after making that replacement, we get an equivalent equation. So that tells me that this graph will have symmetry about the line theta equals pi over 2. Okay, now let's check for symmetry about the polar axis. For the polar axis, we have a couple of options, but I'm going to go with the first one. We're going to replace r theta with r negative theta. So really nothing happens to the r, but it gets replaced with 2 sine of negative theta. Okay, again, because this is a, I'll put a little check there to show that we have that kind of symmetry. Because sine is an odd function, this becomes negative 2 sine of theta. Now this equation is not equivalent to this one. For example, if I were to plug in a value of theta, then the corresponding value of r would be different than if I plugged the same value of theta into this equation. Here I get the opposite of what I would have gotten. So this shows that we do not pass the test for symmetry about the polar axis. Now I'm going to comment on that in a minute, because failing a symmetry test doesn't necessarily think what you would expect it to mean. But let's do this last test right here. So now it says the graph is symmetric with respect to the pole if replacing r theta with negative r theta yields an equivalent equation. So this time it's not theta, it's r that's going to change. So I have negative r equals 2 sine of theta. But again, this is no different from this, because if I were to divide both sides of this by negative 1, I get r equals negative 2 sine of theta. The same thing I ended up with over here, which failed our symmetry test. So this is saying that we failed the symmetry about the pole test as well. Okay, so what this means for this polar equation is that if I were to graph it, I should expect to see the graph have symmetry about the line theta equals pi over 2. It should look like something that has symmetry about the vertical axis. But, and this is kind of the frustrating thing with these symmetry tests, the fact that the graph, the equation failed these two tests actually means that the symmetry test was inconclusive. So that means that the graph of the function or the equation r equals 2 sine of theta may or may not have these types of symmetry. So passing a symmetry test guarantees that kind of symmetry. Failing a symmetry test means the test was inconclusive. It doesn't rule it out. Now, it turns out that the graph of the function or the equation r equals 2 sine of theta really does only have this type of symmetry and does not have these two types. We're going to see that in the next video because we're going to graph this equation. But you need to remember that failing means inconclusive.